Okay, so far we have been going in increasing order of strength. So first, London dispersion forces, which are also called van der Waals forces. That's the lowest. Then dipole-dipole interactions. That happens when you have a polar molecule that's mixing with another polar molecule. Next, we had hydrogen bonds, which are really a kind of dipole-dipole, but they're so important we're going to pull them apart and treat them as a separate category. Hydrogen bonds are one of the strongest IMF, but it's not the strongest, okay? The strongest intermolecular force is ion dipole. This happens when you have an ion such as chloride or sodium and you mix it with something polar, okay? So this is what happens when you mix like ionic substances into water. Just to be clear, this is a negative charge and this is a positive charge. And so we'll notice that the water molecules are orienting differently depending on which charge is in the center. So chloride is negatively charged, so our partially positive sides of water are all going to be facing towards that chloride. No oxygens pointing towards the chloride because the oxygens are partially negative, and that would not be an attraction. That would be a repulsion, right? So when we look at the sodium, the opposite effect is seen. We have a negative charge because sodium is positive. Okay. This is called hydration, by the way, or if it's water. If it's not water, we call it solvation, like solvent. Okay. So, I don't know if you've ever been to a really nice Italian restaurant, or maybe this is how your family eats. If so, I'm jealous. But a lot of Italian families and restaurants have like a dish of really good olive oil, and they put like salt and pepper and garlic and, you know, all kinds of stuff in there. And if you really look at it, all of the salt and pepper sinks to the bottom. It does not dissolve in the oil. That's because salt is ionic, of course, right? Salt is ionic and oils are nonpolar, okay? So oils only have London dispersion forces, so they won't mix with ionic substances of any kind because the charges are not compatible, essentially, okay? So no, salt will not dissolve in oil. It will dissolve in water. Okay. So one thing I like to do is compare different properties of substances to get at the underlying intermolecular forces. Because really, anytime a question is asking you for why a substance is in a particular state, or why something has a particular boiling point, or why it mixes with something, those are always going to be answered with intermolecular forces. Okay, physical property questions like that, always going to come down to IMF. So we can compare bonds and IMF just to get a sense of how things are different. So ionic compounds are held together with ionic bonds. So we're talking about solid salts. Okay, they have very, very high melting points. This is why I told you way back in experiment 4 that with ionic compounds, you don't have the choice of having a liquid at room temperature because, well, they're held together really strongly, which means it takes a lot of energy to melt them apart. Even more energy to boil it, of course, right? So this is like lava temperatures or something. When you think about metals, metals are fairly strong. It takes quite a lot of energy to melt them, but you can do it. Even more energy than ionic bonds, which means metallic bonds are stronger than ionic bonds, right? You have to put more energy in to break them apart, which is what you're doing when you melt. Then the bonds must have been stronger. And then we get covalent bonds, like diamond. You have to heat that up really hot to melt it, right? Like, I don't even know if the lava is enough. Someone figured it out. I'm not sure. But it's a lot of energy to separate atoms in covalent bonds. This is in comparison with something held together only with dispersion forces. So when we think about nitrogen or any of the ideal gases there, they are not going to have very strong attractions because they're nonpolar molecules, right? So if their primary interaction is by London dispersion forces, which I said was the weakest, then it's not very difficult to separate nitrogen particles from each other. And so the melting point of nitrogen is very, very low, right? So to go from solid to liquid, you only need to be at 63 Kelvin. That's cold. A dipole-dipole interaction, on the other hand, would be like hydrogen chloride. Not hydrochloric acid, okay, so pure hydrogen chloride. That's melting point is a little bit higher, still very cold, at 158. That's because it's held together with dipole-dipole forces only, which are stronger than dispersion forces, but are nowhere near as strong as even like ionic bonds, which are the weakest bond. And then we look at hydrogen bonding forces. Again, not actually a bond. It sounds like it's a lie. Don't fall for it. Okay, so an example of that would be hydrogen fluoride, pure hydrogen fluoride, not hydrofluoric acid. That has a slightly higher melting point of 190 Kelvin. Still really, really cold, right? So the lesson here is, even though we have the word bonding in it, hydrogen bonds are much, much weaker, okay? All of these are pure substances. The reason that ion dipole is not on here is because that has to be a mixture, and it's harder to compare mixtures to pure substances, so we don't include them here, okay? But it's important to understand that IMF, while they do go in this order, dispersion, dipole-dipole, hydrogen bonding, they are still far, far weaker than bonds actually are. It's also important to understand that the forces that hold things together directly affect the melting points and boiling points and a whole bunch of other things. Okay, there are a multitude of different charts that can help you figure out whether something is, say, van der Waals forces only, or hydrogen bonding, or whatever. So you can categorize these things. I like this one, but there are many. So if there's no ions present, no polyatomic ions, no metals, etc., then you'll go down to the left. Then you have to decide, is the molecule polar or non-polar? So if it's not polar, only LDF, and it has very low energies. This is and this has a range because different sizes and different structures and shapes and things, but pretty much the lowest possible intermolecular force. If the molecule is polar, then you need to figure out, is it going to have hydrogen bonds? And so to do that, you want to ask, do you have NH, OH, or FH? If you do, hydrogen bonds, which are pretty strong. If you do not, then it's dipole-dipole, which are medium in strength in between dispersion and hydrogen bonding. Back up to if there are ions, yes. If you also have polar molecules present, then you're looking at a mixture made by creating ion dipole forces, which are even stronger than the other three intermolecular forces. If the answer is no, then it's ionic bonding, which is quite high compared to the rest of them. Okay, so this is one chart. You can come up with others. There are others. The following slides are definitions. I strongly encourage you to study these, write them down, make flashcards, whatever we expect you to understand what viscosity, surface tension, and capillary action mean. All of these things are things you see every day. Okay? So like, for example, syrup is very viscous. It takes a long time to pour it. That's because it has high intermolecular forces between the sugar and the water molecules that it's made out of. Surface tension. Surface tension for water is very high because it has high hydrogen bonding intermolecular forces, etc. So these are all about the strength of IMF. I like this picture because it shows us something called capillary action, which is another vocab word you should know. You can use it to dye flowers or celery if you want to, with just some water and food dye. So capillary action is how plants get their water. And you can see that the skinnier the tube is, the higher the capillary action will work. So this comes about because the container, in this example glass, in this example the plant fibers, has a strong attraction to water. strong intermolecular force attraction to water. So that's going to pull it up the tubing a little bit. And so this has a lot of implications in botany. For example, the height of a tree depends on how skinny its water tubes are. I'm not using the proper botany terms, but you get the right idea. Okay? So shorter plants are going to have the fatter tubes, which means they can move water faster but not as high. On the other hand, we have this meniscus here, and if you've ever seen a mercury thermometer, you might have noticed that the meniscus is upside down. It goes up. In water, it goes down. And we always measure at the bottom of the meniscus here, and the top is actually what you measure on mercury. And the reason is the edges that we're seeing here vary a bit. You can even see a little bit of variance throughout this little container. The reason for that is different sections are closer to the glass, and the closer they are more attracted. So they're going to climb up over each other a little bit, and that's how you get that meniscus that dips down. For mercury, mercury is non-polar. Glass is pretty charged. It holds a charge, believe it or not. And so it is repelled by the glass surface. And so basically, the molecules at the edge are trying to run away. And that means they end up piling in the middle. Right? So you can have a meniscus that goes both ways. But it's all about the IMF. More vocab. You should know what evaporation and vapor pressure mean. These are nice pictures of them. You should also know condensation. So a boiling point is the temperature at which a substance transforms from solid, nope, that's wrong, from liquid to gas, right? So boiling is from liquid to gas. It's important to understand that this is a particular temperature. So I said it's the temperature at which. When something is going through the process of boiling, the temperature stops increasing. The heat is no longer going into making the particles move faster. Instead, it's going into breaking apart the particles. It's going into breaking up IMF. A melting point is the temperature at which a substance goes from a solid to a liquid. Okay? You should be able to compare them or rank things based on their intermolecular forces. So if I give you a list of substances, you should be able to think about what kind of IMF they have and decide which one will have the lowest boiling point and which one will have the highest, and so on. Same thing for melting point. This chart is a handy reference to tell us what costs energy and what gives us energy in phase changes. So these are all vocab words you should know. Probably you know most of them. You might not have heard of sublimation, which is going from a solid to a gas. And you might not have heard of deposition, which is going from a gas to a solid. But most of the time people know the rest of them. If you don't, just make flashcards. So for any given material, the amount of heat required to go from the liquid phase to the gas phase is called the heat of vaporization. But we can see that that is exactly equal but opposite to the heat of condensation. Same thing is true for the heat of fusion, going from solid to liquid, and the heat of freezing. They're going to be equal value, same gap, but different direction, right? And so when we're putting energy into the system, is the sign positive or negative? And likewise, when we get it out of the system, is it positive or negative? That's a review of Chapter 5. All right. We're going to do this one as the next video.